Hello everyone, I'm Jianhao from Nanjing University. Today I'm excited to present our paper, WarpAttack, which has been developed to bypass code reuse attacks mitigations such as CFI. This is a collaborative effort between Nanjing University and the EPFL. And was completed during my visit to the Hex Hive lab. First, let's look at a real compiler-introduced double fetch. As we can see from the source code, the shared object was fetched once for the switch comparison. However, after compilation, we can see two fetches of this object. The first time for the comparison and the second time for the computation of the indirect jump address. This is a typical double fetch bug where the object is assumed to remain unchanged during the two fetches, and however, there may be a concurrent modification which will make the second fetch incorrect. In this case, the attacker may modify the object between the two fetches and hijack the indirect jump, as the jump address is calculated based on the second fetch. This double fetch bug has now considered as a concurrency bug, but now WarpAttack tries to use this to bypass CFI. Before delving deeper into WarpAttack, let's recall some concepts. First is compiler. Compilers are fundamental infrastructure that translate human-readable source code into machine-executable binary code. As you may know, there's a gap between compiler correctness and the security. Here we have an example where the memory set tries to scrap the sensitive data saved on stack before the function returns. From a perspective of compiler correctness is state store, and the memory set can be removed. But from the security perspective, it is sensitive data scrapping and should be kept. From here, we know compiler correctness does not equal security. The key insight of WarpAttack is also built based on these compiler-introduced security issues. From the perspective of security, such kind of compiler-introduced double fetches can be a weakness of control flow guards, as control flow guards assumes that the compiler will not break the security checks they require. Actually, WarpAttack exploits a misalignment between CFI assumptions and compiler implementations. The second concept is control flow integrity, or CFI. CFI inserts runtime checks to stop any malicious control flow transfers. It has been practical and fine-grained nowadays. However, furthermore, as memory corruption bugs continue to appear and other widely used mitigations cannot prevent or control flow hijacks, so CFI is getting more and more important. The next concept is bound-checked indirect jumps. From the perspective of CFI, we will assume compiler to be secure and expect it will generate a bound-checked indirect jump like this. The index to calculate the indirect jump will be checked before use. And this indirect jump address is saved on jump table, which is read-only which is saved on read-only memory and should not be overwritten. So there is no need to protect such kind of indirect jump. However, compilers are not aware of security boundaries, so it will generate double fetches like this. The double fetch bugs means that one attacker may modify the shared object between the two fetches, which means that he can bypass the check and hijack the control flow, as the indirect jump was calculated based on the second fetch. Now, let's move on to WarpAttack. WarpAttack shares a similar threat model compared to CFI. We both assume as jump attackers with arbitrary read and write and thread controlling. In fact, the only additional requirement is that the attacker needs to one triggerable gadget sample in the form of compiler-introduced double fetch. So how does WarpAttack work? Specifically, the attacker needs to take control of concurrent thread in advance. First, it overrides to ensure that the victim thread does not go to the default branch and prepares the control object with malicious address. Then it waits for the victim to perform the double fetch, and it attempts to overwrite the risky object within the time window. If the attacker wins the data race, the indirect jump, which is not protected by CFI, will go to malicious target. Then the attacker can hijack the control flow and initiate code execution. If the attacker does not win the data race, and say it overwrites the object before the first fetch, and the gadget code is the variant which is not caused by stack spinning optimizations, then the ROM overwriting will possibly direct the control flow to the default branch, which will possibly crash the program. Okay, now speaking of the challenges of WarpAttack, it first appears in the gadget code detection part. The first challenge is to distinguish compiler-introduced double fetches from normal ones. Our solution is to propose a new binary model to prevent the comparison. Another challenge is the complex data dependency. We propose this by searching double fetches in instruction window of a fixed length, and we have many match constraints to filter out false positives progressively. Speaking of the proof of concept exploit, the first challenge is the short time window, which can be 2 instructions long. Our solution is to put victims and attackers in a loop with different iteration speeds. And the other challenge is the crashes when we overwriting ROM. We overcome this by check the stack content before we do the overwriting. You can find more details in our paper about the challenges and the solutions. Finally, we achieved a successful rate of 0.45 in 20 seconds when we exploit the Firefox, the latest Firefox. Now let's explore how WarpAttack affects real world. In our evaluation of WarpAttack among many real-world programs, we found more than 1,600 victim gadgets in 6 programs, including Firefox and Chromium. We also got acknowledgement from many communities, and we found both GCC and Clam are affected. Speaking of the architectures, although we built WarpAttack just on x86, but we also test compiler-introduced double fetches on other architectures, and we found ARM, RISC-V, and MIPS are also affected. Different from x86 cases, where we have two variants of compiler-introduced double fetches gadget. For other architectures, we just found gadgets caused by stack spilling. In short, WarpAttack affects many programs, compilers, and architectures. In summary, by WarpAttack, we first highlight that the compiler may break the CFI assumption that security checks will be preserved after compilation. And second, we propose a new attack based on that. And we evaluate and show the real-world impact of this attack. Finally, we show a proof of concept exploit on the latest Firefox. That's all of my talk. Please refer to our paper for more details. And I'm happy to take your questions.
Thank you very much. Luca. If you have a question, please come to the microphone. So one of the mitigations you mentioned is having the programmer annotate the security critical regions so that the compiler can, not generate these.
Yeah.
So do you have any idea what it would cost to just have the compiler not emit these gadgets in the first place? So just maybe lose a little bit of performance by not ever having these optimizations?
I think it's like the difference between the assumptions of compilers and security mitigations. So if we want to stop this from the first place, we need to let the compiler know which part of the code is secure and should not be broken. Yeah.
Right, but I meant in general. You could just say the compiler treats everything as being secure and just voluntarily, forego certain compiler optimizations so that these problems are not introduced to begin with. Do you have any idea what the performance impact would be of doing that?
If you stop any optimizations, the performance would be, I think, 4 or 10 times.
Well, but it's a very small optimization you're not doing, right?
Or you mean just stop all the switch jump tables?
Yes.
We didn't how to say, measure that. Yeah.
Okay.
That's maybe an option because if you stop generating switch jump tables, you can also prevent some other risks. So
right. It's probably easier stopping this in general than getting programmers to annotate the code in all the right places.
True. But it cannot stop all because you don't know other optimizations will not generate double fetches. Yeah. Okay. There's no guarantee. Yeah.
Okay. Thank you.
Excellent work. Very insightful. I wanted to ask about the race window that you have.
Okay.
So how big of a race window you have, and I assume that if we don't hit that race window, you crash the program. So
yeah,
that's the sort of the statistics that you uncovered there for the race window, and how you can extend the race window as the attacker to make the attack more practical.
Yes, actually, here our successful rate is based on a very short, or the shortest window, which is 2 instruction long. Actually, you can choose some other gadgets with longer time windows. For example, when there is a jump between the 2 fetches or some function calls, we didn't do that because for the ease of proof of concept. Yeah. But you can choose some other gadgets. Yeah, that's an option.
Okay, so just to make it clear, you didn't use any techniques to try to lengthen the window in your proof of concept attack?
Yeah, we didn't use that. We just performed the proof of concept, and we know there's maybe some techniques where you can slow down the patch table to make the time window longer, but we didn't do that. Yeah, thank you.
Thank you.
Okay, thank you very much. Let's thank all the speakers again.
Thank you.